Let's start. Yes, please. Okay, so thanks everybody for joining us this afternoon. Notice that this is a rescheduled session that was originally set for Friday afternoon. And the discussion topic is perturbative versus non-perturbative approaches. Is quantum gravity perturbative? Our panelists are Jerzy Lewandowski from Warsaw University, Leonardo Modesto from Cagliari University, Jan Pawlowski from Heidelberg University. That's what I'm going to need some help with. Lesław Rachwał from UI's de Fora University, and Arkady Tseytlin from Imperial College. That one I could pronounce. Okay, and the format is the same as we've used in previous sessions. The host of it, me, will give my take on it, and then we'll turn it over to the panelists to make brief presentations, and then we'll open it to everybody for discussions. So my take is, and I'll probably be in disagreement with some people here, my take is it is possible that quantum gravity does make sense non-perturbatively. So the thing that's in gold, established by the grand old men of quantum gravity, is that quantum gravity is not perturbative, by which I mean quantum general relativity, is not perturbatively renormalizable. But I think it could be non-perturbatively renormalizable. And the reason that I believe that that's a possibility is because gravitational interaction energy is negative. I think everybody knows that. I'll give a demonstration of this in my best experimental condition. As things fall down rather than up. Another demonstration of it is that the Earth-Moon total mass is reduced due to gravitational interaction, and that's true even when you take account of the kinetic energy of the motion of the particles. So the total mass of the system is the sum of the masses of the Earth and the Moon minus their gravitational interaction energy, and that's not by a small amount. If you measured in kilograms, that's 6 times 10 to the 11th kilograms, pretty hefty amount. Of course, it's basically a square root in terms of numbers of the Moon's mass, but it's a pretty considerable amount of mass. A more interesting to me example of this is one that was worked out in classical gravity by Arnowit, Deser, and Misner in 1960. It was actually the first general relativity paper that was ever published in Physical Review Letters. And what they did was to calculate the classical mass of a gravitating point charge. And they did it in full-blown general relativity, but they also developed a simple model that would allow everybody to see it in one slide. So I will take the point mass and I will blow it up to be a spherical shell of radius r, capital R. And then I'm going to calculate its total mass energy, rest mass energy, as being equal to its bare rest mass energy plus the familiar electromagnetic linear divergence. But then the extra wrinkle in the theory is we're going to put in the gravitational interaction energy, and that's of course g times some mass squared over 2r. And the only concession that you need to make to general relativity in this special set of coordinates is you need to use the full mass. Okay. And that gives a quadratic equation. As an American, I'm incapable any longer of solving that. But I got a foreign graduate student to explain to them how to solve it. And the answer is m is equal to c squared r times the quantity of a square root minus 1. And that's the exact solution of it. And by the way, that's the exact solution that you get in general relativity, too. Of course, R was just a fiction, put in a regularization put in to make the intermediate steps finite or make them meaningful steps. We want in the end to take the spherical shell down to 0. That's done by taking capital R to 0. When you do that, an amazing thing happens. First off, the result is finite. Second, it's completely independent of whatever bare mass you put in. Contrast that with what would have happened in particle physics. My particle physics colleagues, they would have just said, if they just had, if I could go up here, if they just had this part of the answer, they would have just said, no problem, you just measure the sucker, and then whatever you need in order to get that, you put that in there to be minus that plus that. It works. That's the way renormalization works. Here, that's not what's happening at all. As long as M0 is just finite, you get a result which is completely independent of M naught and finite. It regulates itself by exactly what I said. Gravitational interaction energy is negative. When you have a infinite positive source of it due to the gauge charge, then you get an infinite gravitational response, and the cat chases its tail, and the result is finite at the end. It's way, way, way too big to explain the mass of the electron. If you put Q to be equal to the charge of the electron, then it's the square root of alpha times the Planck mass, but it is finite and independent of the bare mass. Another thing of great relevance to the discussion today is you will not see this if you use perturbation theory. You only see this if you do the calculation non-perturbatively. If you just take the point of view that, we're going to do perturbation theory, here are the small parameters, G and Q squared, we'll expand the square root in those things, then what you get is this series of escalating divergences, plus minus divergences. And guess what? When we do the calculation in quantum gravity, that is what we get. They're different divergences. Quantum effects soften the linear divergence to a log divergence, but that's what we get in full-blown quantum field theory, is this oscillating series of ever higher and higher divergences. Maybe that's what's going on. Maybe if we could just do the calculation non-perturbatively, we would get a finite result. So this opens some glittering possibilities. Perhaps elementary particles are non-perturbative bound states in quantum gravity. So we don't have to do complicated experiments that we can't even actually do to try and scatter Planck scale gravitons. Every measurement of a fundamental particle is a probe of quantum gravity, and a pretty sensitive one. And perhaps even, stuff like the generations are excited states of the first generation. Perhaps the answer to that famous question of who ordered that when they reported the properties of the muon is that it's actually just a heavy electron, like everybody thought at first. Of course, there's a catch, and the catch is that you need to be able to do calculations non-perturbatively, and we can't, at least I can't. And it's hopeless to try and do them in general. To try and calculate it exactly is just lunatic nonsense. But perhaps you don't need it exactly. Perhaps what you need is just some kind of a non-perturbative resummation scheme, so an alternate perturbation theory that allows gravity to catch up at each order with what's going on in the gauge sector. That's still a very, very tall order to develop. People have looked for alternate parameters that they could expand in. I remember Andy Strominger suggested possibly the dimension of space-time. Some other people suggested large n in number of matter fields, et cetera. None of them gave useful expansions. But it's not completely hopeless because you get to pick the quantity. You don't have to do everything all at once. If you want to just focus intensely the community's interest, all you have to do is report one quantity, which we normally would calculate perturbatively, and we get uncontrollable divergences, and you can calculate it in some plausible non-perturbative resummation scheme such that you get a finite one. If you can do that, you'll focus everybody's attention, and then they'll figure out how to do it in general, I guarantee you. Of course, even that's a pretty tall order. And I don't know how to do it, and I'm not going to claim otherwise. I will tell you about how it is possible to do another thing in which you could talk about quantum gravity being non-perturbative, and that is, suppose that we're looking at cosmology. So we're dealing with an expanding universe with Hubble parameter h and first Lorentz parameter epsilon. Then there's a phenomena that we all know that is that inflationary particle production, which in de Sitter goes like HA over 2K squared, and will be comparable to that in any inflating geometry. It is, a staggering amount of particles. That's the amount of particles in one wave vector. One wave vector, and last time I checked, there's lots of different wave vectors. Notice also that it has the property that the occupation number becomes of order 1 right when the when the particle is near to experiencing horizon crossing, that is when k over a, the physical wave number, is equal to the Hubble parameter. And that's a hugely important fact for our purposes, because it means that these are infrared effects. These are not hard ultraviolet effects. You don't even have to worry about what's going on, whether there's a c squared term or an r squared term or lots of higher derivative corrections. You can get this just like John Donahue gets corrections. John and Buren Bohr get corrections to long-range potentials. You can get them completely reliably by using quantum gravity, I mean quantum general relativity, no frills, as a low-energy effective field theory. Suppose you believe in string theory, it doesn't make any difference. As long as your string theory has general relativity as a low-energy effective field theory, you would get the same result. And let me give you an example of types of corrections you get. Oh, by the way, notice another thing. The number is growing. It's growing staggering. Partially misleading because the 3 volume is growing as well, and the thing that measures the strength of quantum effects is the number density of virtual particles. But even the number density is growing, albeit much more slowly, and that leads to effects which in flat space would have just been constants to acquire a secular dependence. They grow with time. So a particular example in a recent paper that I and let's see, Shumpei, who's here, I think, and Nick Zamas, who's directly in Crete, did is we looked at the result of taking a massless minimally coupled scalar, coupling it to gravity in de Sitter background. That's epsilon equals 0 and h is a constant. And we calculated one loop corrections to the Newtonian potential, same way that John did long time ago in flat space. And what we get is a result which takes the form of the classical result, just de Sitterized so that every factor of r gets an a to become physical length. And then it has a correction which has long been known from flat space. I think that was first calculated by a student of Schwinger named Radkowski. And then the new thing that we're interested in, oh, by the way, kappa is 16 pi g. It's the loop counting parameter of quantum gravity. And the new effect that you get in de Sitter background, which is because you've got a new dimensional parameter. See, in flat space, you're kind of screwed. The result at loop order has to go like powers of kappa, and the only thing that you can balance it with is r, so that means that in large distances, it's falling off. Not true any longer in de Sitter. You've got a new dimensional parameter, h. You can get corrections, you can and do get corrections that go like kappa h squared, and in particular, they grow with time. And that opens an amazing possibility, which is that that loop counting parameter, kappa h squared, is a very small number. If you take the numbers that we believe about primordial inflation, kappa h squared would be quite a small number, 10 to the minus 10 or smaller, depending on what the scale of inflation is. That, by the way, is not bad. That makes perturbation theory, at least at the beginning, converge like a bat out of hell. So that's good. But of course, the effects build up with time. And eventually, if you have a very long period of inflation, they build up so much that the logarithm of A overwhelms the loop counting parameter. And then perturbation theory is breaking down. And that's what I mean by non-perturbative resummations of effects. It turns out you can resum this effect, and the resummed result has recently been done also in a paper by Shumpei and Nick and myself, and that's the resummed result. Okay, so maybe
what is psi?
Psi is the Newtonian potential. So it's the analog of 1 over r, gm over r for a point mass. So you put in a static point mass and you ask what's the gravitational response to it.
So there is this kappa squared term is missing here. So you need to add extra terms in the pre-exponential.
What happens is that if you just expanded this guy out, you'd have that guy in a series.
Yeah, but this term is missing.
He's asking about the second term, the kappa squared.
Oh, yes. I'm sorry. That one, the resummation is only a leading logarithm resummation. I should have been clear about that. Thank you for pointing that out. It's just like, in fact, it uses the renormalization group. So it's just like renormalization group. It only captures the leading infrared logarithms, the leading large logarithms at each order. Anyway, so I think that's interesting. And I will close with that with a question to everybody, and that is, can we resolve anything beyond effective field theory? So, of course, if the initial speculations about particle masses and everything being non-perturbative quantum gravitational effects are true, then the answer is yes. These things, though, that I've been talking about, quantum cosmological things, are all done in the context of low energy effective field theory. And they're not really, they are non-perturbative resummations, but they're not looking at what's not being done is to resolve the ultraviolet problem. The ultraviolet problem still remains, and it's no worse and no better than it ever was. All that's happening is that we're resumming strong infrared effects, which, however, have the property that they're completely reliable predictions of the theory. And my question to the panelists and to everybody else is, if the initial speculations about being able to generalize this ADM calculation to quantum field theory and getting the same physical result turn out not to pan out, will we ever be able to see anything beyond just corrections, these large infrared corrections in the sense of low energy effective field theory? Because if you look at the power spectrum, it's already a pretty small answer, and it's not got any secular dependence at tree order. There are loop corrections that would be down by another factor of kappa squared h squared. Strangely enough, there may just be enough cosmological data available in 21 centimeter cosmology if we can harvest it all. That's a big if, no guarantee, and I won't live to see it in any case, but some of the younger people here will, to resolve the one loop effect. So it is possible, in principle, to resolve the one loop corrections. It may be that that's all we can ever do in quantum gravity, or it may be that we can do something beyond that. And with that question, I will invite the panelists now to give their take on the various issues. And let's see, two of them were good enough to give me slides. And let's see, I'll go first with, oops, does it look right? What's that? Murphy's Law. If anything can go wrong, it will go wrong. Well, I think I succeeded in doing something wrong.
You just click away. That's the cross on.
What should I click on?
The cross on the right upper
Right
corner. Close it.
Please go ahead. You know how to do it. Okay, so now we want to see the slides that were given to me, and let's see here. One of them, one class of them. Screen sharing has been stopped, so I need to restart it.
Yes, just go through.
Go ahead.
Yes, double click.
Here.
And that's can
Make this bigger.
no shut.
Sure. Okay, Lesław, I think you're up there. Let me see if I can make it bigger yet. Go to one. Control S. Okie doke.
Is it possible that you turn 90 degrees in your computer? I can do. I don't want to have to talk to the.
I can handle that screen. Old-fashioned technology involving the two hands and the arm.
Yeah. So thank you very much for the invitation to this panel also. So I want to tell you something about what is my take on whether we are perturbative or non-perturbative in quantum gravity. So I can go to the first slide. So okay. I first tell something about perturbative one, then I will tell about both, and then you will see what is my position here. So first we can think about perturbative things, and that's how we school simple-minded do, that we take some equation of motion, we look for the solutions, so for the minimum, we do some small perturbations, and then we try to see what's the reaction of the system, if this is how we try to probe the system. And for example, here there goes an assumption that the space-time, when there is no curvature, so the flat space-time is a state without any gravitational field. And then what you do this way, you get something that at least you promote the definition that we can get a graviton, but then I have to add two adjectives, that this is a pure graviton or a bare graviton. And then it's something that with this adjective, it suggests that this is not a physical thing. But at least we can define it mathematically, and we can use the rules of standard perturbative quantum field theory, and then you can try to go on and do something like that, this kind of quantum field theory, perturbative quantum gravity. And what I can tell you, it's just an estimate. I don't have a very good quantifier, but 95% of the standard model is also perturbative. So we are not doing something completely strange. It's very much in lines of quantum field theory. And in this way, I said that something like 95% of the standard model works. There are some effects beyond. And this is a very good accuracy. Why? Because we can ask first approach why we see the interactions between elemental particles and gravity. We say that the gravitational coupling is small. And how you can see it, you see at the bottom of the slides, there is this very primitive thing. You have the gravitational vertex, some massive particle, and then the attached wavy line of the graviton. And very roughly, if you ask how this vertex goes, it goes either energy of the particle over Planck mass, or if you want to have some static particles, you say mass of the particle over Planck mass. And if you look at the spectrum of the standard model, almost all the particles which are there, if we don't think about UV completions, they have masses much smaller than the Planck scale. What does it mean? It means that this vertex is very perturbative because dimension less coupling constant which enters this vertex is much smaller than 1. So this means that mathematically you have a parameter in which you can expand. So okay, this is something for the perturbative one, some part of the motivation. Now let me tell you something also on the other side. There is a famous non-perturbative approaches to quantum gravity, like loop quantum gravity, spin foams, and there are also many others. And what they will tell you, and when I was a student, I heard many times, because I was in Warsaw University, maybe later Jurek can also support this point of view, that we know that exact solution in GR, they show non-perturbative behavior because the equations are non-linear. We have a lot of self-interaction even in classical gravity. So this kind of approach that you try with the vacuum and you try to linearize may bring a lot of artifacts because you are trying to say that this non-linear complicated self-coupled system is mimicked by doing something to the linear order. And when we know in mathematics you can produce a lot of artifacts just because of this thing that you try to promote a different structure. And then I'm coming back to these two adjectives that I put to my gravitons, because the bare gravitons, they do not exist in nature. And this we also have said in a talk and discussion with Jan, that they have to be dressed. They cannot be, we are basically now with political correctness, we cannot speak about bare things, and the gravitons also cannot be bare. It has to be with clothes. Otherwise, we are breaking something. So this is the thing that we know about graviton. You can ask how thick is his cloth, because it can be small, it can be much thicker. It could be a jacket like for the -20 degrees winter. But here, this is a question how we describe the effects of the dressing. Some people, and that's what I heard, even when I was a student in Warsaw, they say, look, gravitons are such a concept which uses perturbative approach in non-perturbative theory, and they do not exist at all. But this is a very extreme point of view that quantum gravity is by definition non-perturbative, and you cannot even speak ever about gravitons. I don't agree with that, but I tell you what I have heard some years ago. And this also mathematically goes to the problem, because when we do perturbative theory, of course, it's not just the first in order, but then you can try to go to higher, and then you can ask the question about the convergence radius. And typically in situations that we have in field theories, this thing is non-finite. Sometimes it can be even 0. So it's not something that you can transform a whole complex plane if you consider the sheaf of the perturbation theory. Here might be might be non-convergent at all. It's just asymptotic here, but still you use it. So this is a good mathematical question how you can do this, but and this comes with the fact that we have nonlinear theory to start with. So maybe this idea to linearize nonlinear theory is inherently wrong, because you see, we know this already on a classical level. And I told you about this 5%. They are effects in standard model which are very pronounced, which have to do with QCD, with instantons, and for example, meson masses that come because of non-perturbative effects. So we cannot say, although when we look at the coupling constant in standard model, they are all perturbative, but it doesn't mean that there are no effects. They are non-perturbative effects even in the standard model. So this is something that I estimate like a 5%. And then I can ask which kind of effects I could think of non-perturbative nature in quantum gravity. If you are more philosophical, then you can ask even the very simple question: why does space-time exist at all? Because maybe the Hilbert space without any space-time would be much simpler. So this is a question, the whole existence, which is a question 1 or 0, and then we know that the answer yes, space-time exists. So this is a good question, and I would say the answer to this requires a lot of non-perturbative thinking. And another effects that we know, and these are very in comparison with the standard model or standard quantum field theory, for example, instantons. We also expect that this kind of non-perturbative configuration, and then you see on the formula how they depend on the coupling constant. You see that these effects can also probably appear in gravity, and they are the name of people who first studied, they were Eguchi and Hanson. So this is something that you can also expect this on the same level like in QCD. You know that they are these instantons, and when they contribute, for example, to the masses of mesons, and in gravity you cannot exclude them, and they are non-perturbative because they go like, if you try to expand this function, it goes, actually it has a analytic series which is all with zeros, but still the function is non-zero. So you see this is completely non-perturbative thing, non-analytic in a sense, and this is one of the effects that we can expect in quantum gravity. Others that they were also mentioned in this conference were changes of topology. When we do perturbative quantum field theory, it's assumption that we start with some flat spacetime, and basically all the structure that you put on this flat spacetime cannot change. The perturbation cannot make it different. So if you start with some topology, it cannot, in the process of even resumming all the perturbative corrections, cannot be different. But there were many motivations from other people here at this conference before, and they say that they are possible in quantum gravity, in full quantum gravity topology changes. And then if you want to describe this, again, you need you could say this is non-perturbative effect, because perturbation theory never would see it. Even if you resum all the orders, you will never see the topology changes. So this is something, and let me tell you back to the situation with instantons. In quotes, we can also say that it's all exact solutions that show the nonlinear structure, like for example black holes, they are also non-perturbative, and then you can do something in a mixed style because you can put the quantum fields on a curved background. And what does it mean? It means that some part of your gravitational field you sum exactly because you use classical solutions of the classical theory. But so this is, let's say, non-perturbative part. But at the same time, when you have quantum gravitational field there, for example, on a space-time of the black hole, you have part which you treat perturbative. So I would say that, you see, this is one of the examples of the formalism that you have both perturbative parts and non-perturbative parts at the same time. So, of course, you can be a bit ambiguous about the splitting, but this is possible still. So it's not only that either perturbative or non-perturbative, the answer is not 0 or 1, the answer can be also 1/2. So this is what I wanted to say, but let me continue. These non-perturbative methods, they are useful for understanding quantum field theory, yes? Because we can know everything by just doing coupling expansion. This is analytic structure of quantum field theory, but we know that there could be something non-analytic, and then this non-perturbative method tells us exactly about that. What's the very simple way? If we have some coupling and we used to work in perturbative framework, then you could say, and this is a very fun idea, you can use duality, and then you can go to one of the inverse of the coupling, and then if the original coupling was not perturbative, then the inverse may have chances to be perturbative. So this is one way how to kind of overcome the problem. If you don't have perturbative quantum field theory, you can go to the inverse coupling and it will make it perturbative. The question that I posed here is that very similar to the question that you have seen yesterday, why we look for some non-perturbative effects. If maybe the goal here, although I don't know if this, even if achieved, it would satisfy everyone here, that if we find perturbative renormalizable UV finite unitary quantum field theory of gravitational interactions, why do we need something more? Probably we need something more, but one of the things is how to, in such framework, look for the non-perturbative effects, because probably there will be also of our interest. And so I motivate that non-perturbative techniques, of course, they are very useful. We have motivations for seeing non-perturbative effects in quantum gravity, and for example, in a non-perturbative RG community that I also come from, it's very important that some things cannot be, especially couplings, cannot be small. We have to be able to describe the situation when they are, let's say, of finite value, not necessarily perturbative. Of course, you can reach maybe some situations by perturbative approach, and this is important if you want to define non-perturbative RG or situation with fixed points and generally the flow near them. So all this is important for one of the approach to quantum gravity, which is with the words asymptotic safety. But let's say this is just a method. I also put a question whether we have some fundamental non-perturbativity, right? Yesterday we spoke about fundamental discreteness. Here there could be the similar question whether we want fundamental non-perturbativity, in a sense that it is not just a method. Maybe the nature is from the definition non-perturbative, and then how we can understand this and whether it makes sense to speak about perturbative quantum gravity. Although, of course, I don't know if the speaker of today morning is here, but we have seen very nice seminar by Emil today morning, so I don't want to say, but if this would be true, then probably all of your talk would have to go to a not very nice place, let's say like that. But of course, it was a very nice presentation. So let me just finish with some questions. No, I think that still we can make sense even with everything what you presented or what everything else we speak in a perturbative language. And then I will show you one direction of the arrow, because I'm claiming that if you have any almost any perturbative computation can be given a sense and meaning in a non-perturbative way, but this doesn't go the other way. So of course, if you have something non-perturbative, you may not ever understand it in a perturbative language. And this is a very simple formula that I could even show to children at high school. But when you see this is a definition, and then on the left-hand side, you have something that you can compute, let's say, perturbatively. If you know how to take derivatives, you can compute the left-hand side from the formulas that you memorize, you cannot compute perturbatively. But look what's on the other side. On the other side, you have some definitions which uses the limit. But for having this, you have to know the knowledge of the function everywhere. So basically, this is a non-perturbative part. And this equality tells you that basically you can understand everything which you know perturbatively in a non-perturbative way, because you just take limit at the end. So that's what I'm also saying, that if we have some good gauge invariant observables in perturbative quantum gravity, I think we can always find the meaning of them even in a non-perturbative way. So it's not that they are completely lost even as an artifact of perturbation theory. I said this arrow doesn't go all the way, all directions, only one. If something is completely non-perturbative, probably it will always stay as there. And then we know that in almost any quantum field theory, there are both perturbative and non-perturbative effects, and QCD was the example. Probably the same we expect in quantum gravity. And maybe the question is whether there is some fundamental non-perturbativity, but the people who work, for example, in loop quantum gravity, they could probably tell us this, but let's wait and let's see for the answer. So I think with this, I can finish.
So the only other person who sent me something was Professor Living Pawlowski, so let's see, how do I?
And there are two things.
Maybe he's wrong.
Maybe he mixes up.
It's not connected.
Yeah, I'm not sure.
It's not connected?
No.
I think you mixed up with the slides.
It's a very, all these Polish people. And honorary Polish.
No, you are honorary Polish.
No, there's lights with this.
Yeah, I think it's here.
Maybe Pawlowski then.
Pawlowski.
Oh, that's a very good pronunciation. Wow. Better than mine.
Forgive me,
No,
so, let's see here, I just need to enlarge it. Oops, no,
that's the wrong direction.
but it's the other way around.
I'm Mrs. Lawrence.
Yes, please. You know what to do, Not sure. Okay.
Okay. Yeah, so I just my presentation will be very short, so you should see that I like photos. That's a photo I took yesterday during the barbecue, and since I'm running away after this panel discussion, I used the panel to thank the organizers very much for this. And I think it was very non-perturbative in a sense, so I got a lot of new ideas, which I wouldn't have got by not being here and having the interaction also during the barbecue. So for me, it worked very well, and also evaluate these meetings by the number of ideas and the number of things I learned, and I learned a lot and have a lot of new ideas. So thank you very much. Okay, let's come to my one slide. I give a definite answer, not like in the last panel. Yes, whatever this means. And this actually, I think, is the problem. Let's talk about perturbative quantum gravity. So we can do perturbation theory in most of the approaches we have. Maybe we have a perturbative expansion, diagrammatic or otherwise, about the ground state. But that's already a problem because we first have to define this ground state. In standard quantum field theory, we just take the ground state of the free theory and we expand. Then we have resummation schemes, which we usually don't call perturbative because it's a Padé resummation or whatever of the coupling we have. We can also do a saddle point expansion, but now we are entering already slippery ground because you can ask the question, is the Schwinger pair production a perturbative effect or not perturbative? If you measure in terms of what usually is called non-perturbative, namely e to the -1 over coupling, it's non-perturbative, but you can just compute it with one loop perturbation theory. So it's I think it's a not that well-defined distinction, and I totally agree to what Richard has said about non-perturbative effects in one sense, but the Schwinger pair production would actually fall into this class, and it's one loop perturbation of the you compute the one loop effective action of quantum electrodynamics and you have it. So non-perturbative quantum gravity, and I think quantum gravity is non-perturbative, but you know it's a easy formulation. In most of the approaches I know, you need non-perturbative expansions, computations. You see already, I mean, I foliated this a bit, A and B, also in discrete approaches like lattice quantum gravity, causal sets, and so on. You have some statistical aspect in it in order to compute. So the two fall certainly in the class of non-perturbative computations, but now I can expand the point C under perturbative quantum gravity. I make a saddle point expansion about something like an instant point, gravitational or otherwise, and instantly I get effects which you would call non-perturbative because you can't cover them by perturbation theory about the trivial ground state. So, which means the whole thing mixes a bit. And this is also, I think, a common topic in all sorts of physics areas. If you find the best representation where the ground state already covers quite some of the physics, or the ground state you expand about, you can do perturbation theory even in a setting which otherwise you would have to compute non-perturbative. Okay, so again, my answer is yes. whatever it means. And I think what it hints at is we should find optimized schemes, which means we all have to understand more about the underlying dynamics of the theory. And I actually like very much this last thing, the picture of the conference. It's a quantum gravity foolscap. And you see, I mean, there are lots of different aspects of the foolscap, so the bells of the foolscap. And you have to take into account that the fool in medieval Europe was somebody who told the truth. Okay, so maybe we are all telling aspects of the truth. Okay, that's it.
Okay, neither Professor Modesto or Professor Tseytlin sent these slides, but they probably have comments that they want to make illustrated on Blackboard. So let me kill this and let's see. You're first alphabetically. Why don't you go ahead?
Okay.
Should I?
So
I can do it.
first of may go ahead. Okay. To me, actually, about this kind of the title of the panel, I don't see that tension between the perturbative and the non-perturbative approach. As long as it's not really necessary to go beyond into a non-perturbative. So let me recap a little bit what is the problem. The problem again is that we have 4 fundamental interactions. 3 out of the 4 are perfectly consistent. They are good theories at quantum level. In the perturbative approach, what I mean by perturbative approach, what we have to compute technically, we have to compute Green functions and point functions. That's what we have to do. So you have a classical theory, which is defined in terms of the action, and you can find solutions of the questions of motion. That's done eventually. At the quantum level, we can formulate our theory throughout the path integral. And throughout the path integral, you have to compute the Green function. Okay? So now, the Green function in the path integral approach is the functional derivative of the exponential plus the coupling with the external coupling. That's the problem we have to. So now we have to compute this quantity. Okay. Are you able to compute this non-perturbatively? I will be very happy to see that. In the electrodynamic case, in scalar field theory, in electroweak theory, we don't have this. We don't need to go beyond perturbative. We can just make what? The loop expansion. We make the H-bar expansion. Okay, we can do more, but it works till now at least. Let me complete and then I will be very short. So we have one technique I like to advertise, the book Binder's Audience of Shapiro book, chapter 2 for everybody eventually. And there you can find the perturbative expansion in H-bar. And you compute your corrections to the classical action, and you get the quantum effective action. That for me is not the effective. We can discuss later. I don't love too much the effective theory approach. But the quantum effective action is the result of this integral at the perturbative level in the loop expansion. What usually happens is that when you make this computation, you emit divergences. That's the UV catastrophe. Okay? Feynman came and said, okay, for electrodynamic and for the whole standard model, we can figure out a way to hit this divergence. And everybody seems, maybe not everybody, but most of the people were happy with this and are still happy with it. For gravity, I mean, for Einstein's theory of gravity, this doesn't work so easily. I mean, it's not a good theory at quantum level, and technically it's not a normalizable theory. So now you can say, what I can do now? Maybe I use another expansion. I don't make an expansion in H-bar, and I solve the path integral exactly. How? Maybe solving the vector-rich equation or Cauchy equation. There are other proposals. Eventually, I'm not so nice. Or even for gravity, I want to say, no, I want to, since for 3 interactions it works, why for gravity doesn't work? It's exactly like electrodynamics. There is no difference at the quantum level. It's just a spin 2 particles, and instead of a spin 1 particle. Okay. Let's do it. With Einstein gravity, we agree there is this issue of normalizability. Let's do the same in the past people did with the weak interactions. We upgrade the Fermi theory that was, like Einstein's theory, not normalizable, to an IVB theory in which you have a vector boson, but that's not enough. We introduce the spontaneous symmetry breaking, and everything works perfectly. We don't need to stop to Fermi theory. We can just go beyond Fermi theory, and with another action, slightly more complicated, we solve the renormalizability problem. And 3 out of the interaction works so well. It's not a guiding principle, but it works out well. It works well out 3 out of 4 times. The proposal for me is that we have to take another action for gravity. And we have to be consistent with not only normalizability, because Einstein is unitary and we all agree on that, but also with unitary. So this theory can be quadratic gravity with some smart prescription. This theory can be theory with higher derivatives, can be even weakly non-local, or any other proposal which is in this framework consistent with the fundamental mechanics. So this is to me the beginning and the end of the story. Of course, we would like also have information that the non-perturbative theory to solve the path-integral non-perturbatively, and which is equivalent to solve the Vecchiarich equation eventually. Fine, I'm not against. What I'm doing is what at the moment I'm able to do, and it seems to work quite well, regardless of what a lot of people told us from in the last 40, 50 years. Although the Cousins paper on the local theory and Stainless theory and others of this proposal by Shapiro and people were on the table. Okay, that's the comment.
Okay, last, but thank you. Not least.
Yeah, I'm the luckiest one because I don't have much to say, and a lot of ground was already covered. So maybe I should emphasize that progress is not done by discussions of problems, but also by developing new methods and tools. And remarkably, in the last, 20 years, there are lots of developments of various tools in quantum theory, plus in string theory, I mean ideas of CFT duality, but in supersymmetric theories, which of course are just models. There is localization, bootstrap, also matrix models in two-dimensional gravity, which could be modeled by matrix models quite successfully, though the meaning of it is not completely clear. So going backwards to Toft, in fact, one of the first quite non-trivial, non-perturbative methods which was suggested is one-over-n expansion, which is very useful also for two-dimensional models, for four-dimensional models. And Toft expansion is remarkable in the sense that the claim is it's actually convergent perturbation theory. So usually you need to add usually get asymptotic series in coupling, but in you take say n=4 supersymmetric Young-Mills theory, which is kind of very ideal theory, and do Toft expansion there, you get functions of Toft coupling, say one some anomalous dimensions or well-defined quantity, which are well-defined, have finite radius of convergence, and then you can expand them at strong coupling if you can find them exactly. And integrability, that's another development which happened in the last 20 years in gauge theory, observing that certain anomalous dimensions are described by integral spin chains, and in A-4 theory that becomes kind of quite well-established tool. Integrability allows to compute these functions exactly for certain operators in planar limit. Then you can expand them in strong coupling, a strong large lambda coupling, which is non-perturbative from weak coupling limit point of view. And you discover they match predictions which you get from string theory in some curved space. So that's quite remarkable. And where is quantum gravity in this story? And the answer is, strictly speaking, nowhere. It's string theory living in curved space, but it's planar limit. Planar limit means that you don't have gravity loops. But what I want to emphasize is that hidden symmetries, well, supersymmetry is important in this story. Integrability is about hidden symmetries. They may allow to do things which may look completely impossible from perturbative quantum theory point of view, which is not, in principle, not even well defined if you just do perturbation series. So if something like that can be applied to quantum gravity, that would be big progress. And first, of course, we need to define what we mean by perturbative and non-perturbative. So once we have, if we have dimensionless coupling, it's kind of clear. We say we can have non-perturbative factors we discussed already in field, in energy, or in dimensionless coupling. In gravity, we have dimensional coupling, so it's energy versus Newton's constant, or scale versus Newton's constant, curvature scale. So you need some dimensional parameter to say what is small, what is large, of course. And that's where part of the problem, and part of the problem with definition of what is perturbative and non-perturbative quantum gravity is, actually. But I guess I just finished with saying that we need new methods which would be applicable to quantum gravity. And there are certain lessons in string theory and relatively recent lessons, which is not just about finiteness of single scattering amplitudes. It's more about non-perturbative aspects of string theory, which may be useful to get some insights into quantum gravity. I guess I stop here.
Okay, thank you. Ladies and gentlemen.
I have a question to Arkady. Can you give some example of non-perturbative method which you have in mind applying to gravity?
Well, in the context of string theory, there are string theory depends a lot on these non-perturbative effects, like if you, well, this is not a big sort of intuition insight of few people in 1995 that you need also solitons in string theory beyond just perturbative spectrum. D-branes, they are non-perturbative objects. It's like saying that monopoles are important, and indeed in equal theory, it has duality symmetry. And duality is essentially G into 1 over G's. That was actually referred earlier. For that, you need to know that there are monopole and dyons in the spectrum of this theory, which are non-perturbative objects. So string theory incorporates gravity. So non-perturbative effects are important in string theory. That would be my answer to that question. But a simple kind of clear-cut computation, which will have some bearing to just Einstein gravity, that is obviously tall order. Though I would say black holes were mentioned, but black holes are, in a way, solitons of Einstein theory. And they are supposed to play a huge role in, say, scattering at large energies and all that. How to make these computations precise, that's where we need some models tools. And that's where the string theory insights may be useful.
Yes. Little.
There's no follow-up or?
Please go ahead.
Okay, so this is sort of and again, I might wade into controversy once again, but this is to do with so in perturbative approaches, when you're starting off with some background and then you're constructing your gravitons from graviton field from the perturbation. The question that came up last week, and I just want to ask the panelists what they think of this. Do you think that the graviton has to be a sort of, I mean, a collective excitation in the fundamental non-perturbative theory, or should it be, in fact, a very fundamental part of the spectrum of the non-perturbative sector of your theory? I think this kind of question came up in some form last week, and so if we're talking about perturbative and non-perturbative, in one case you have gravitons. The question was always, what is that graviton state in the non-perturbative or background independent way of doing things? And so what is your opinion, and this is to any one of you, of what that state, if that graviton state should be, would it be okay for it to be a collective excitation of your fundamental degrees of freedom, or however you would wish to call it, or do you expect it to be, in fact, some special state on your fundamental or non-perturbative theory?
I mean, there's certainly, in my opinion, a state which, if you look at low energy scattering, can be described in terms of graviton scattering. And if you look at this state, there will be a massless excitation. Okay, you can then call the graviton or not, but it will, just by definition, and that has not even something to do with being perturbative or non-perturbative, it will not be well described in what we usually call a graviton, namely an expansion, a fluctuation about a given vector. Right? And you have a nonlinear symmetry, which means that if you have some object or field which behaves nonlinear under this symmetry, it will not stay. It's very simple. Okay, but so it has nothing to do with perturbative or non-perturbative. It's just the question of how to define
linearized or non-linearized theory.
Yes, and there will be state, which is obviously non-linear in this, whatever you expand about, right? And there will be limits. We know it very well. In this room, closed flat space, and we can define gravitons or gravitational waves. Okay? And the spectral answer is also clear. At least the minimal mass mode we know, it's massless.
Leonardo had a comment.
I think let's say maybe the graviton to me is the solution of the linearized equation. Right? It's the spin two particle. But maybe your comment, the first part of your comment.
I just mean that in the state,
the ground independence issue.
Yeah, and also in the full non-perturbative theory,
Right.
do you expect this to be some special state in that theory? That's the question.
At classical level, the ADM formulation tells you what is the spectrum of the theory. And, the same you see at the linearized. The ADM formulation of Einstein's theory.
I meant in the non-perturbative quantum gravity.
Well, you can. I don't know. At perturbative level for sure, you cannot generate the other degrees of freedom. At non-perturbative level. There are examples of theory in which the spectrum changes with at quantum level in perturbative level. So you have to.
But there will be a massless excitation, right? So it's not even talking about going to some non-perturbative regime. The question is, do we have a state in the spectrum which has mass zero? And the answer is yes.
There's clearly a state. The question is more that in what. It's like asking for description of a collective degree of freedom. Can you think of a graviton as a collective degree of freedom of some more fundamental theory? And that's the question. Or you think it is a fundamental degree of freedom? Okay. No, that's basically the answer, right? That's what I'm asking.
But you were asking also about the background issue.
Last week we had this question
about this. But to me, let me make just a short comment. In any interaction, there is this issue. Not only gravity. Gravity derives proper background is eta mu. Usually, because we are able to make the computations, you have Lorentz invariants, you can define the particle, etc. But even in standard model, eventually we can ask the same question. No? Usually, you expand around zero, right? Around phi equals 0, a mu equals 0, the gluon equals 0. But why not in a room which is filled very high energy electromagnetic fields? You can. It's more complicated. And so they should be there. Moreover, all the results are background independence in the proper formalism in gravity. So you get perfectly covariant theory in the end, using the background field method, technically speaking. Further,
As you just said, to define gravity on a particle, you need to decide about the
yeah,
vacuum. The definition of vacuum is not consistent with any diffeomorphism invariance in a way, because you need to decide what are your boundary conditions to talk about scattering problem, like was discussed in Tseytlin. It's hard to define what you mean by a matrix.
Sure.
Yes, so in that sense,
in Minkowski's matrix is very
yeah, yes. But once you say Minkowski, then we need to decide what is diffeomorphism invariance and what we're talking about. Of course, we can define diffeomorphism invariant quantity.
Look, I think that there's also, there are different layers of problems we have. So the first one is also at the very end, maybe you want to make contact experiment, right? And there it's a very practical question. So now I'm taking my practical hat and forget about mathematics. When I look what the LIGO people are doing, this is Minkowski. They measure something in Minkowski background. That's not completely true. Mathematically, it's wrong, right? But it's experiment to good approximation. It fits.
The classical.
No, I know, but I mean that.
Well, at LIGO is not quantum.
We of course can discuss for centuries about the question: what is the ground state of quantum gravity, or of one formulation of quantum gravity? Or we can just go more to the practical side and ask, can we compute something? And that's for all approaches, and it's extremely difficult, which has the chance to be measured in a sense beyond the classical level. And Guy and I had the discussion yesterday. So the question is not so much whether something is non-perturbative or not. The question is more, can you compute it? So if I have an approach which is pristinely non-perturbative and has everything in, but I can't compute nothing. So I can compute nothing. What is this worth? Except of having some mathematical description. So I think I hope I read what you say. Right? And there's
nothing is worth nothing.
If you can't, from the mathematical point of view, maybe not, but from the uses for physics. And I'm now, very rigid now.
In that case, then the regime in which you're trying to describe is a physically determined regime. That's fine. But then when you're talking about the non-perturbative regime, then we shouldn't be. Why should the non-perturbative regime enter into description of gravity waves?
That's why I made the Schwinger effect example. So if you give me a good expansion point / good state, I can expand my physics about. In most cases, this will be perturbative. So, which means that the question whether something is perturbative or non-perturbative, duality also go into it. If I find a duality formulation of a strongly correlated system, strongly interacting system, I can use perturbation theory. So does it now mean this is a perturbative problem or is it a non-perturbative problem?
I think I could speak to that just in terms of dimensional parameters, right? The coupling constant of gravity is going to be G, and it needs an energy squared or something in order to be dimensionless, right? So suppose that we're interested in measuring some quantity, and it depends upon this. And suppose that the sort of naive result is F0, and we're looking for a series. It matters a lot about whether we expect it to be perturbative or not. If we expect it to be perturbative, I would say it's hopeless. Because we're going to, if we solve the ultraviolet problem, we're going to get some number. It's 10 or 100 or maybe even 1,000 if we're lucky. But this number, even at the biggest accelerator we could ever build, the biggest accelerator that all the governments in the world together contributed to build, this effect right here would be down by a factor of, I think, 10 to the human measurement has ever been that accurate. And I think the most accurate measurement is 16 decimal places, something like that. Gio might correct me, and we'll never measure that. So if it's perturbative, then we'll never see even one loop quantum gravitational effects ever. It's only if it's non-perturbative that we have a chance of seeing quantum gravitational effects, at least at low energies.
I guess in that formula, there must be H bar in the denominator.
Yes, let's see here. So,
Now we're talking business.
yeah, now we're talking energy. So, let's see, H bar goes like a length to the third over a mass times squared. E, last time I checked, it goes like G, length squared over time squared. And G goes, sorry, that's G. And H bar goes like a mass times the length squared over a time. So if we have something like this combination right here, then with that thing squared, then yes, we have to have a 1 over H bar to make it appropriately dimensionless.
These are-
No, that's a little bit misleading because then in classical limit that will go up.
Yeah.
But no, because what you
Depends on how you count G.
Yeah, what you put in the numerator. Actually, the simplest is to express it in the wavelength. So the wavelength of a graviton versus the Planck length. So that's the simplest because then you don't have to worry.
Okay, same difference. It's
The alpha gravity is
same difference. It's going to
alpha
be
gravity
G
L Planck
over
squared
some
divided
length
by
squared.
That's right. Exactly.
And
Yeah, L Planck squared.
And the point is that the smallest wavelength we can get, and the biggest accelerator that's ever been built, will make this number 10 to the minus 32 or something. That's just hopeless. We'll never measure that accurately, or maybe the beta reticulans will come down and they've measured that accurately after a billion years of technological development. But our species right now in the next century is not going to do that.
So unless they are extra dimension. If they are,
That's right.
Yeah.
So there has to be some kind of a change of this paradigm. If we stick to this paradigm, we're screwed.
We know that
That's the way
we should split this question into a sub-Planckian and trans-Planckian question, okay? I agree. I mean, we will certainly not measure trans-Planckian energies in the near future.
Well, but there is another alternative. Like, suppose that this ADM effect that I mentioned is right, then it's giving the mass starting out going like 1 over the square root of G, not analytic in G, and then you could hope to measure it. If you had terms that involved inverse powers of G or logarithms of G or something, then it's in principle possible, but I think it's only if it's non-perturbative that you're going to be able to do it at low energies. The other option is just perturbative at very high energies, those of primordial inflation.
Still, I want to make this distinction. Of course, I mean, in the effects we will have a chance to measure I mean, at least in my lifetime, quite some lifetimes after that, are sub-Planckian effects. Okay, and there the question is, can we see anything from quantum gravity? But there's also the question of the UV closure. And that's definitely a trans-Planckian question. You may say it's just a mathematical question, but nevertheless. So
No, it's just a mathematical question, but suppose you solve it, you're either going to get a perturbative series that goes like this, or it's going to have some non-perturbative things in it, like inverse powers or logarithms or things. If it has inverse powers or logarithms, then I think we might be able to see it just numerically. If it's going to be just a perturbative series, if it resolves itself the same way that Yang-Mills did, then I'd say we're just screwed. We'll never see it.
that's true. Still, we have the closure question and whether we can distinguish the different closures, and that's a trans-Planckian question. And there the coupling G times E squared is either big or settles at some value. And then the question is, do we have non-perturbative effects there? Can we do some duality transformation that we can take a perturbative series?
Yeah, that is, could we get something that has 1 over G's in it?
I'm talking now
that's the
about
whole
G E squared. If I take the Newton constant in the infrared being big, I'm talking about trans-Planckian effects.
You're talking about making E big, right?
Yes.
Absolutely.
And then the question is, in the different approaches to quantum gravity, do we have non-perturbative effects in this regime? Can we resolve them either by brute force crunching them down, or by being inventive, having a duality transform, knowing a good state to expand about and so on. So this is for me the question about being perturbative, non-perturbative. And then the other thing, I mean, for me, as the simple example is just as I said, the Schwinger effect. So do we see something non-perturbative, and that's what you are after?
Yeah, something that goes like
where the-
inverse powers of G or square roots or
Yes.
logarithms,
Yes.
something like that.
So these are these two aspects, and I think you were also more asking about the second aspect, right? Because that's the question that, I mean, below the Planck scale, I can use the graviton as a good degree of freedom. Right? That's clear. Above the Planck scale, there's this question, but still there's a state which has a spectrum.
Sure, yeah,
Right?
no,
And
that's
this must be
sort of
singled out. So if you give me a theory of gravity which has no massless asymptotic state, I mean, you better dump it.
But I guess we can still anticipate and accept that there is a possibility that there is a cutoff which is not Planck length. In that case, staring at an Einstein theory is not enough. Or just simple modeling, have R plus R squared plus whatever, infinite series with some cutoff, which is not Planck. That theory will have nothing to do with that.
Yeah, you're right.
And it's not.
Starobinsky theory is like that.
No, it's not just one R
The
squared.
Starobinsky massive.
You need, if it's a cutoff, it's infinite series, it's some effective action.
You don't have to specify the theory. It's the question, do we have a scale of new physics?
Yes, exactly.
Then,
Yeah.
of course, it's a new game.
Yes.
So
So
what
this is,
about the,
Yeah, and that
what about the species? I mean, we know that we know pretty certainly that the cutoff, if you have additional particle species, the cutoff comes down.
Right.
So in the standard models, we have about 120 particle species. So we know that, strictly speaking, cutoff cannot be the same as in pure gravity. So already there, we know that the cutoff is smaller than the Planck scale.
Sure. The loops, wind up getting
But the loops
contributions
you
to
could resum, as I said,
each
but the
matter
black hole.
species.
You know, a black hole tell you. The loops you could imagine resumming or fine-tuning, for example. But the black hole is the one that is not fine-tunable. Because if you have a black hole, because black hole operation is democratic in species, you know that the black hole smaller than that cutoff scale cannot be thermal. And that's end of the story. So you don't know what is up there, that you don't know, but you know that the standard theory cannot continue beyond that. So from that point of view, black holes are more reliable. But yeah, they match the same argument. So the normalization also points to the same direction. Right. So yeah, for example, that we know in string theory is also a perfectly nice example of when cutoff for sure is below the Planck scale because of if string theory is weakly interacting, the cutoff string scale is below the Planck scale.
in string
But you
theory,
can have it above the Planck scale, and then you just enter an asymptotically safe regime.
You need a string scale above the Planck scale.
Yes.
Well, in string theory you cannot.
Oh, you can.
Well, unless you
If you want to stay perturbative, no. But
yeah,
if
you will hit the strong coupling.
Yeah, exactly.
But then you need to
But this is, you see, this is a technical limitation. I mean, you're saying, okay, I want to stay perturbative, then I know.
No, it's perturbative. Okay, when we say perturbative, we are a little bit diminishing the role of the strong coupling because you see, when the theory becomes strongly interacting, so field theory starts from degrees of freedom, as you said, right? So now the degrees of freedom are well defined when they are weakly interacting. There is no such thing as well-defined, strongly interacting degree of freedom. Because when the degree of freedom becomes strongly interacting, it means that you have to change the regime of the theory and go to new degrees of freedom, like in QCD, right? In
Yeah,
QCD,
but this is more a matter of description of the theory. There I
but
agree.
it's always a matter of description.
No, but still in QCD, even in the strongly correlated regime, where it's better to go to current correlation theory and so on.
Exactly.
Right? I mean, you still can, if you are dumb, describe your theory in terms of gluons and quarks.
No, it's impossible. I mean, it's
Oh,
practically.
what do you mean? I mean, that's what they do on the lattice. I'm
Right,
sorry.
that's-
No, what do you mean? I mean, so if you have a power to solve your theory
Yes.
non-perturbatively
Yes.
in strong coupling,
Yes.
then you are solving it. Then you don't need to mention degrees of freedom. You just solve your theory. But what I'm saying is that to describe your theory as theory of quarks and gluons at 1 kilometer distance it doesn't make any sense because they don't exist at 1 kilometer.
If you
Yeah,
want to
so-
say it does not make sense to write down a low energy quotation effective theory, which only has quarks and gluons, I completely agree.
Well, we know that. I mean,
Yeah,
I'm
no,
not saying something weird.
There's nothing to debate.
This is, yeah, so that's what I'm saying. So, I mean, of course, you can always say, oh, but maybe I can have a like most powerful computer in the universe and I continue to solve my theory.
I repeat what I said. So, I mean, with the statement about the string scale being above the Planck scale is a statement you just want to describe a theory from the top to the bottom by the same degrees of freedom. Then you need the string scale being below the Planck scale. I completely agree.
Exactly. So, in other words, as I said, theory, the label of a theory comes from what are the degrees of freedom and how they interact. Now, the string theory, degrees of freedom are string excitations. If you want to continue describing your theory as string excitations, then better they be weakly interacting. Or you may have some power of duality. That's a different story when you somehow map weakly interacting on one clade in the sum with none. Otherwise, you will hit this wrong. Now, by the way, there is an nice example of when we sort of brutally go to strong coupling. That's M theory limit. In M theory limit, that's precisely what you do. You decouple strings, and instead D branes become perturbative out-of-line state. And guess what you end up with? You end up with pure supergravity in that limit. So you have 11-dimensional supergravity in that limit.
And it should be clear that, I mean, this is call it a community thing. So as you saw now, for me, having the string scale above the Planck scale only because then this would be, I mean, what comes out then is a strongly interacting theory. It's not a restriction per se. Because maybe, I mean,
well, it is in the sense that you no longer have a theory. Then you should tell me what you have.
Let's assume, I mean, we find out because we have infinite energy at our command. We find out it's a string theory, and we find out the string scale is above the Planck scale. Then we just are unlucky in nature, and we have to compute a strongly interacting, a strongly correlated theory.
But okay, sure, but how are you changing? What does it mean? So the string scale, we know what we should see when string theory would interact. For example, we had made predictions even at LHC. If LHC miraculously hits the string scale, you're going to see string resonances. And there we can predict what you're going to see very, very strictly, what kind of spectrum, what kind of resonances, in what they decay.
I understand now, the underlying.
Tell me what you're going to see, then tell me when would you conclude, what would be the experimental outcome that would tell you that the string scale is above the Planck scale. What is the experiment?
Oh, I may see non-trivial resonances as I see mesons also in experiment. And if somebody would tell me,
but about
it's the theory of quarks and gluons, and then see mesons, I first had to say, okay.
But about the Planck scale, first you have to hit the Planck scale. If the string scale is above the Planck scale, first you have to hit the Planck scale. Now, once you hit the Planck scale, you start producing already strongly interacting gravitational resonances. Then you start producing black holes. Now, then I don't know what it even means to produce a string excitation in that regime. I don't know, but
that would be the task for string theory, not mine.
Then that's what I'm telling you, that in that regime, string resonances, we don't know how to describe them. I mean, that's all.
Okay, there are other questions and comments.
I have a follow-up here. That's, I mean, coming back to the original question of Samut, yes, I agree with what we said, that we have the graviton in a spectrum, just that maybe I wanted to, together with recent remark by Gia, that we have to understand it in a limit when the coupling goes to zero. Otherwise, if it is not in this limit, even value of the coupling is finite, still we cannot speak that there is really the spectrum. And this is how it works in QCD. Although in nature we have quarks and gluons that have finite couplings, but to speak about the spectrum of QCD in the sense of quarks and gluons, the coupling has to go to zero. So not only the condition that we are below the Planck scale, but also the gravitational effect which dimensionless coupling also has to go to zero. And then we can speak about the spectrum and the graviton is there as a massless particle. Otherwise, it's a fuzzy.
In QCD, I better don't go to coupling zero to talk about the spectrum. Because I would never see a measure.
I don't have to go to exact zero. I don't see why. As long as theory stays perturbative coupling, you can.
Yeah, but it also depends how you define the the perturbativity of the field. I mean, you can say that there is some convergence radius, yes, but it may happen that the convergence radius is 0. I mean, it happens even quite often. And
Okay.
then
Yeah, that's a fair thing. But look, so normally in physics we go like we try not to bother unless theory really presses us to bother, right? So, for example, in standard, when we teach quantum electrodynamics, right, we say, okay, look, now we introduce a photon. In the previous semester, you had classical electrodynamics. You studied classical electromagnetic waves. Now we tell students, okay, now those waves are coherent states of photons. So degrees of freedom are photons. Then we do certain limits. We say, okay, now I can derive Coulomb law as a one photon exchange. Okay, and so this sort of illustrates that quantum theory works because the first test of quantum theory is that it correctly recovers the classical theory. Now, then we do exactly the same for gravity. In gravity, we say, okay, no, now we introduce spin 2, we quantize it. Now we do one graviton exchange that recovers Newton's law. Now we do nonlinear correction to it that recovers Mercury per helium precession and so on. And that's why we think that we are on the right track, right? So that tells us that we are not completely crazy to quantize gravity and that because it works. At least.
what I was saying, I mean, I agree completely with you that we see this first exchange, then exchange with loops, but how mathematically they should be viewed? They should be viewed as terms of the series expansion, but the series is at 0.
Well, this is what I don't understand. Why it has to be at 0? It's sufficient that it's perturbative.
Maybe we distinguish again. I mean, situations where we have the scale of new physics, and I mean our scale of quantum gravity, below and above the Planck scale. So in string theory, we have it below, which means I don't have to discuss at all such a scenario. In most of the other approaches we are discussing here, the scale is above, which means we have an inherent need to discuss this non-perturbative regime of gravity. Okay,
this is precisely my problem. This is the problem of language, because in the description, so on one hand, this is what I don't understand, because on one hand you are saying, and as if we both are saying the same thing, you are saying graviton is the degree of freedom, in the weak coupling it's well defined. Now, if we start from there and go bottom up, then at the Planck scale, latest at the Planck scale, this graviton will become strongly interacting. So therefore, how are you going to continue beyond that while still talking about graviton? I don't understand.
It's the same way I go to low energy QCD and still talk about a gluon.
But I told you that doesn't make any. I don't understand how
it's not the question whether it makes sense. It's the question whether I can describe the experiment we have in low energy QCD with that, and I can grant you, yes, I can.
So, okay. For example, if you do scattering of pion scattering at 1 kilometer, you can describe that as a theory of gluons?
I'm just saying I can describe this in QCD where I still have the gluon hanging around, but if I'm not completely dumb, I also introduce pions. Yes, I can do this.
But they cannot coexist. It doesn't make it. So pion is a composite of quarks and gluons. You cannot simultaneously have an effective theory in which your degrees of freedom are pions and also quarks.
Definitely I can, and most people have.
Then you have invented some.
And I can define in a mathematically pristine way a path integral where I couple both a quark operator to my current in the path integral and bilinear of the quarks or some enhanced thing. This is possible, and this is also what is usually done if you not go to the lattice straight away and crunch down your.
But perhaps we are talking. Probably you are right, but I'm not.
I hope so, because otherwise I can.
Because what you are saying, for instance, the least it will contradict to A theorem, because A theorem tells you that the number of degrees of freedom cannot increase when you go to infrared. But now, if you have quarks and gluons, and then you go to infrared, and on top of them you also have pions and bunch of.
So I can grant you that what I'm doing is fully in line with the A theorem. The only thing I'm saying is that if I look at the path integral, I have source terms, and it's up to me whether I couple a quark to the source, and additionally also a q bar cube. That is not that is not against the A theorem. I mean, otherwise something like 2pi effective actions and whatever would be against the A theorems, and of course they are not. It's just the parameterization of my theory. So I know what you mean.
I don't know. I mean, perhaps I'm misunderstanding what you're saying because
I think you're not in a disagreement. You're just talking
Yes.
about different.
probably we're talking about something.
I'm saying the whole time. So, I mean, I completely agree to your point of view. If one is entering a strongly correlated regime of the theory, you better have the methods at hand to solve it.
And so you have a method to compute quark scattering, gluons and quarks.
I have a method to
at large
compute-
distances.
I have, I mean, clock scattering at large distances obviously does not make sense, but I have a method to compute pion scattering in QCD in an approach where the degrees of freedom which I have in my effective action, beware of the fact I'm not saying one should add some degrees of freedom which are not there, are just also pions. Or call it collective degrees of freedom, which have the quantum numbers of a pion. Okay. But I mean, we are now in QCD and talking about specifications in QCD. So what I'm saying is, I mean, the approaches, I mean, apart from string theory, we are talking about that the scale of new physics, if you wish, is the Planck scale, because then you have to do something about gravity. It will not be described perturbatively in gravity, and that's what the people are working on. I mean, I hope I described correctly.
Let me make one more attempt and then I shut up because so one more attempt would be, let's take a standard model, right? So in the standard model, how everybody was expecting to discover Higgs at LHC, because Higgs was necessary for unitarizing the strong coupling of longitudinal W bosons. Okay, so if I simply take standard model and I simply throw away the Higgs, the longitudinal W's become strongly interacting around scale of 700 GeV or something like that. Okay, so therefore we knew that there must be new physics that unitarizes. Now this is Higgs. So then when Higgs enters the game, what happens is that the longitudinal W's that we thought were strongly interacting at that scale, actually they continue to be weakly interacting. Why? Because the Higgs creates necessary unitarization, and so the theory continues. So therefore, so some people were asking this question, what about graviton? They were saying, okay, look, graviton becomes at the Planck scale strongly interacting. Maybe there are some new degrees of freedom that we can integrate in, and so graviton stays together with them, but then graviton becomes weakly interacting. Sure, if you have such a theory, that may happen. But
look, I mean, yeah, I completely agree, but let's assume we don't know it. Right, and I take now again the QCD analogy. So somebody tells me in the ultraviolet, I go to LHC, I make high energy experiments, I see gluon jets, right? So I extract from this, okay, I have a theory where there's gluons, then there are quarks, okay, because I also can identify them. So now I take this theory and I go to the infrared. Maybe I don't have experiments there, right? I just go to the infrared and I see, hey, this theory becomes non-perturbative. I set my task, I mean, I set my mind to it, I solve the task, I go to the lattice or whatever, and I crunch down the theory and I see, hey, this thing has colorless excitations, pions, sigma modes, and so on. And then I know, after I have seen it in my approach, oh, I better reformulate the whole thing. That is why I said, I mean, having the right ground state is solving half of the theory. I better reformulate QCD in the sector in terms of pions and other mesonic degrees of freedom, because that is what is running the show. But I have to come to this conclusion.
But you are not answering the question about
I'm doing
about
it.
your theory. My question was, you are saying that in your theory, graviton hits the strong coupling at the Planck scale. Yet some kind of scale of regulator is sharp. And my question is, what is your theory in between? What are the degrees of freedom?
Yeah, I mean,
so
first, first we walk, then we run. So what we are at the moment in gravity, I mean, in asymptotically safe gravity, is we know very well. So the graviton becomes non-perturbative, but if you look around it, most of the rest of the theory seems to be very perturbative. Which means now we can really go.
I don't understand the sentence. What does it mean? If graviton becomes
the Wilson coefficients, of the operators are essentially canonical. So there's no anormal scaling. So the only thing in the effective action of asymptotically safe gravity, which will be scaling with a huge anomalous dimension, is the graviton. And all the other terms we have looked at are scaling perturbatively, which means, if you wish, in my opinion, I cannot answer your question because we have not done it. We are very close to a reformulation of asymptotically safe gravity in terms of a weakly interacting theory. But at the moment, we are in the status where I would just take, again, my effective action in QCD, run down, and I get something highly non-perturbative. I can solve it, but now I have to just understand what we see. So that's my opinion of what we are in asymptotic safety, which of course I know best. But now I go to the other quantum gravity approaches, and from my asymptotic point of view, for example, in causal sets or also in lattice gravity, the same is tried. You first try to compute some observables or some expectation value in order to get a clue what is going on. Would be the same.
These are very fascinating. Look, I don't want to diminish the role of these fascinating ideas, but I think we have a misunderstanding of what it means to have a theory versus some really inspiring, fascinating idea. I mean, you can. Ideas may be very spectacular. I don't want to, and of course, all of us are thinking about this and that. But from what you are describing, you are in the process of an attempt. You don't have a theory from what you answered.
No, I disagree. We have a theory, but I mean, we don't have to discuss.
Then we are calling theory different things.
Can I ask a question? Can I compute in string theory at high energy? Does it make sense or not? From what I hear, it seems doesn't make sense. I go to infinite energy. Does it make sense or not?
In string theory?
In string theory.
Well, I mean, yeah, that's a very good question. So in string theory, as in any other theory, there are domains of calculability. In those domains of calculability, we can do calculations reliably. For example, in string theory, we can do different amplitudes. Even at, for instance, Transplanckian energy scattering or string scattering Transplanckian energy, we have done it. Actually, two groups have done it with the same results. Multi-string scattering amplitudes can be computed reliably. Of course, there are also regimes in string theory in which the string coupling or the toast coupling becomes strong, and there we don't know how to compute things, just exactly in the same way as in any other theory. So yeah, so the status of the string theory is not some kind of obviously some magic. We can compute, and usually we do that. We try to compute what we can, and then make predictions. So this is what we.
No, I agree.
So this is what we do.
But the quantity is not GE, but it's GE over B. If you are a large impact parameter,
exactly.
Even if you go to high energy,
exactly.
still
momentum transfer is the parameter.
So it's nothing to do with the Planck.
Absolutely, yes, exactly. Absolutely.
I have a question to Arkady. Can one use string duality to compute something non-perturbative in gravity?
Well, string duality, unfortunately, is just limited to BPS states. Well, reliable computations were done only for BPS states, something protected. You try to go beyond that, that's where the models like ankle force with Young-Mills, ADS, that's where there is some playing ground with that. But if you really talk about strong weak coupling duality, unfortunately, we don't really have tools beyond localization. But localization is about certain supersymmetric quantity, like Wilson loop, which is supersymmetric, or some partition function on this free sphere or something, S4. Which you can compute exactly in lambda NN or G Young-Mills NN, and then you can see whether on the inversion it's invariant. And there are examples of it, but this is for very specific quantity. If something like scattering amplitude of some graviton, that's beyond what is available. Even in perturbative string theory, you can ask what happens if you scatter gravitons at low energy, but you go to all orders in string coupling. The series presumably is not convergent. So you will need some deep brain corrections to that, or de-instant corrections to this scattering amplitude, which is non-perturbative in string coupling. And yeah, but the short answer is probably no, at least beyond the protected ones, or what is controlled by localization.
Questions, comments? Issues that people wish to raise? Yes, please.
Maybe I can open different kind of worms. Kind of triggered by one of Jens' slides. So how sorry, yeah, the one slide. Kind of how non-perturbative do we expect things to go? Like, is it really, I have a perturbative sector, then I have an instanton e to the minus 1 over g squared, another perturbative sector plus another instanton. So is that all there is? Do you expect that? Or is there something even more non-perturbative?
Depends again on the approach to quantum gravity we are talking about. So in asymptotic to safety, as I said, I expect a minimum non-perturbative nature. This is what we also see in the computation. And I would also say we have results which are extremely stable, and I would say they are apparently converged. And it's not a perturbative series, so you have to be very careful with your systematic error. But so concerning the existence of the theory, I think these results are very stable in pure gravity. And there we see a very short, if you wish, non-perturbative regime about the Planck scale, where the running turns from perturbative to fixed point running, and there are only 3 which really are relevant and non-perturbative. And the rest is perturbative, and I don't expect this actually to change. I mean, we have talked about gravitational instantons, for example. We have also looked at those contributions, so I don't expect this to change if I take topological configurations. But keep in mind, I don't expect this, so this is actually an open direction.
I have a follow-up question. What should be computed in order to verify your results are correct in this small non-perturbative stream? Is there any measure of like maybe next order contribution or something which you can estimate and show that?
Well, that's why I said, I mean, for me, these results are, I mean, concerning the existence of the theory. I'm not talking about the unitarity and so on.
No, I'm also not about unitarity. I'm asking, you do some computation. So what is your check that your computation is correct? Normally, if you do some expansion, you check that the next order term is smaller than previous term you are considering. But what should you compute in your methods?
Well, what we compute in this method, so in most cases we do a double expansion. One is in terms of vertices. Now we are talking about scattering vertices of gravitons. And that does not mean that I assume that the graviton is a good asymptotic state. I assume it's a good off-shell state. So if I want to do diagrammatic expansion, what I need are the correct off-shell degrees of freedom. That's not the same as asking, is the graviton a good asymptotic state? So that thing, and then we have scattering vertices of these objects, shell gravitons, and they better are localized. Okay, so what we can't, what the expansion is not really good in, is if you have a vertex and this has a resonant channel, like in QCD, a pion channel in a four-quark interaction, then this has to be accommodated separately. But if you have vertices which don't show a large angular dependence and decay in momentum space, that's perfect. Because the only thing we have are one loop diagrams in these full correlations. So if we look at gravity, we go to the lower lying vertices in gravitons, and we see precisely that. Right? And we can also match this with similar expansions in theories which also have non-trivial momentum dependencies like QCD. And in gravity, the situation is even better concerning how local these objects are. Okay, and then you go to higher and higher correlators, gravitons. If you talk about pure gravity, and you ask yourself whether the results converge. Right? So there is a systematic expansion scheme. It's not like in perturbation theory, but keep in mind also in perturbation theory, it's an asymptotic series. And so we call this apparent convergence. And this has been really tested thoroughly in asymptotically safe gravity in the last 25 years. So we look at the expansion, in the expansion of these scattering vertices, higher and higher powers, and we look at the curvature invariance. Okay, and that's the reason for me saying that if I look at all these different operators, these are two very different directions in correlation space. They are converging quickly, and the Wilson coefficients, I now take the language which has been used here in the conference, are very trivial. Right? They essentially, I mean, you get canonical running of your couplings. And that's a good sign that these operators are pretty trivial, and perturbation theory in these operators is a good thing. So you have a small non-perturbative section, and we have this very well under control, and you have a larger perturbative section. That does not answer Guida's question, but I think for me, and you may disagree there, or others also, this answers the question whether this quantum field theory as a non-perturbative quantum field theory exists. Keep in mind, again, I make this very clear, it does not mean it's a unitary quantum field theory, but it's just a quantum field theory. That now the hard work starts, you have to tick the boxes which we want to have for physical theory. Right? So it's not about an idea, so the theory exists. I think this is, for me, beyond reasonable doubt, but it does not mean it's a physical theory. And that's what now has to be checked. And the best way to check this is, of course, to find a reformulation of a theory in terms of fully weakly. That would be novel.
Are you saying that if there is some condensed matter analogy to that? So you have some system and you discover there is a non-perturbative fixed point in a theory which you thought is unitary at some limit. It's actually non-unitary. So is that, I guess it's possible.
It's possible. It's possible.
Theoretically, in condensed matter, certainly it's possible.
Absolutely. That's why I say, I mean, the existence of a theory is one thing, right? It's being unitary, and of course, in gravity, it's
then the question is whether theory prefers to live in this fixed point, whether this is the meaningful starting point.
Absolutely.
So is it the one theory or many theories, class of theories?
It's a class of theory in the sense that we see different fixed points. I mean, if you have fixed points where quite some of the couplings have large critical exponents, you usually either have it's an artifact of your truncation, or you haven't found the right degrees of freedom yet, so you cannot claim that you have convergence. Right. So in the standard approximations to asymptotically safe gravity, we have an order of 4 or 5 fixed points. So 3 of them don't look good. One is what we call the Reuter fixed point. That's what usually is called used as asymptotic safety. And then there's another one which is very close to R-squared gravity. So in a way, we have some understanding of the fixed point manifold. But whether this is really the full fixed point manifold or not, I can't say. Because we have a very limited, of course, approximation to the effective action, which is designed, of course, to find this asymptotically safe fixed point we would like to have. We can't say anything about the full fixed point manifold. And the one we like and want to have is the minimally non-perturbative one.
Leonardo, I have a comment about unitary request for you in asymptotic safety scenario. So you said, as far as I know, also that you have a theory, I mean, you know what is more or less the theory at the fixed point, right? So why you say you can claim unitarity or not? You have the action at the fixed point, which as far as I remember is quadratic action. So naively, I would say it's not unitary, no? But maybe you have something to ask.
No, so we have an off-shell description in order to find the effective action. And the graviton works well as an off-shell degree of freedom. It definitely, if you look what the graviton propagator looks like, and now again, worked out in flat space, it's, you see, if you look at terms of gauge theories with linear and nonlinear symmetries, there are two examples. One is the photon and one is the gluon. And the photon has a nice, call it interpretation as a physical particle. So the spectral function is a nice one, right? It has some rule. The gluon has not. And the graviton falls more into the class of the gluon. And that the gluon is not a nice physical particle. It has nothing to do with confinement. It has something to do with the nonlinear symmetry here, right? So, and the graviton falls more into the second class. So unfortunately, though it's a good off-shell degree of freedom, it's not something, if you look at states, which you can use for states. That's the same if you wish in infrared QCD. I happily live with the gluon actually in infrared QCD. It's not really relevant, but it's also not having a nice spectral representation as an asymptotic state. But I can use it to get my chiral perturbations. So in my opinion, it's not unbiased because of my QCD background. We are in this situation now in asymptotically safe gravity. We know from this off-shell expansion, it works, but we haven't found what substitutes the infrared graviton as a good degree of freedom in the ultraviolet. Okay. And one has to really, distinguish in such a diagrammatic approach between off-shell degrees of freedom. You need to run your Feynman diagrams, if you wish, and the states. Right?
But in the end, you have an action, no? Which is R plus R square plus R mu square.
Yes.
Because you said this are the other sublimiters are marginal.
Yes. But
so if you look at this action, you cannot claim anything about the spectrum in your free. You can write down the propagator and actually, yes.
I can write down the graviton propagator also in R² gravity, but it's not a gauge, the diffeomorphism invariant object. So what is its meaning?
In quadratic gravity, it's clear that there is a spectrum and there is what we will till now call ghost, and then there is a unitarity issue there. As long as you do not introduce some prescription or something.
If I look at the gluon spectral function, there's a ghost state. Does it mean that QCD is non-unitary?
QCD is unitary, but there is no ghost state. Where is the ghost state?
Oh, I look at the spectral function of the gluon.
The classical theory is fine, right?
Classical is fine, but the quantum theory is not.
Yeah, but non-perturbative.
And I can expand. I can write this down. If I want to write down a classical action which fits the non-perturbative gluon, it's a piece of cake.
So
you will have a ghost state.
Because you mean you have this complex conjugate ghost in the effective theory, the infrared, right?
It depends. Even you may have complex conjugate poles, or you may have a spectral function which is negative, and so on. And so on.
Indeed, I'm quite confused about the results people get in QCD, but I understand your point. You have these corrections such that the gluon does not have any more, is not any more massless in the infrared, right? This is what
that's not even the point. If I go to the ultraviolet, there's Zimmermann, and the gluon spectral function is negative in the ultraviolet because of perturbation theory. So it has nothing to do with mass gap in QCD and so on.
QCD, the ultraviolet should be unitary for sure.
Yeah, you see. So the gluon spectral function in the ultraviolet, if it exists, is negative. Okay. So I would straight away, assume with the same right as the ghost states, obviously.
But how is this consistent with Tarkovsky-Katz rules in QCD?
Well, because the cut rules, you can only, if you look at the mathematical background, you can only use them if the off-shell degrees of freedom belong to on-shell, existing asymptotic states. So you can't do this strictly speaking, you can't do this in the gauge theory.
But there are different requirements for different spins.
Yes.
So the gluon is spin 1, and that's, also, by the way, that's related with why you can have repulsive spin 1, but you cannot have repulsive gravity.
I know that there are loads of layers of complexity, right?
Well, for spin 2, I think it's very strict. The spectral function has to be positive.
No.
What do you mean?
I'm
No?
sorry.
Then you have some kind of pathology on the complex plane. Unless you are changing quantum field theory.
Okay, we are again entering. Sorry about this kind of. I'm sorry also because I have to go away now. It's the right point to go. Yes, I'm saying. Otherwise, I'm not asymptotic.
If you have a negative spectral function, that's good to know. That's. So
no.
If you are saying you have negative spectral function, that's okay.
Wait. There are two spectral functions for the graviton. The one is the off-shell one. Actually, it's the one of the fluctuating graviton. That one is actually positive. If you take now your effective action, the difformism invariant, which comes out, and you look at what we call the background graviton, it by definition has a negative spectral function. But I'm not too much worried about it. The one which is affected by the Pawlowski rules is positive. That's why I also said, one has to be very careful there. People always just apply pre-level, which in this theory is just simply not true. Okay? So the off-shell graviton, which is running around the rules, and if you have Pawlowski rules, and there you would have complex conjugate poles, would screw up the theory. This has a positive spectral function. Okay.
If I take fully non-perturbative 2-point function,
yes.
Not 3 level, just fully non-perturbative.
Fully non-perturbative 2-point function, which is, wait a second, which is running around in the loops, has a positive spectral function.
Yeah. Okay. So then you have positive. Then because I thought you said
no.
You said that
that's the one which, if you don't have this and you go to the S matrix and you use Pawlowski rules, that would be really a problem. Now you go to the effective action, which is not the one if you take derivatives of the background, the background independent effective action. That's not the thing you put into your S matrix, because there you need the off-shell degrees of freedom if you have scattering already at 3 level. If you use this background independent effective action and you take derivatives, then you can define a graviton propagator, which is not the one which tells you how quantum gravity fluctuations really propagate, and that has a negative spectral function. So there are two different things.
I'm totally confused.
Yes,
you have your operator.
I have to leave you with your confusion.
No, but I thought your goal there was to clarify some confusions. Otherwise, yeah. But I don't understand now. You have an operator, right? So you have operator which we call graviton.
Mm-hmm.
So then I take 2-point function out of that operator.
Wait a second. You have a diagrammatic approach, and
forget about diagrams. I'm not asking.
Let me finish. And there we compute the graviton propagator, and that's also the one you have to use if you want to compute S matrix elements. And this object has a positive spectral.
Yeah, I don't know if that. I was just asking. It's absolutely basic. I was saying you have a well-defined operator. You said, which you call graviton operator. That's an operator. Now I can compute correlator between these two operators. Fully non-perturbative, but 2-point function.
Yes, and this has a positive.
Okay, but that would be the answer. But you are making it more. You're saying there are many layers.
Good answers usually have layers. I'm sorry. It's a complicated theory. I'm sorry.
But that has a positive spectral.
Yes, that's the thing you put in S matrix elements, and beta has a positive spectral function. Has a positive spectral function.
No, it better have, but does it have?
Yes.
Okay.
I told you several times.
Okay. No, I'm not sure because you are going back to ghost. Then you mentioned some ghost. I don't know why, but you came back to you said PCD has ghost, but that's okay, and then you come back. If it's positive, it's positive. Then I don't have any complaints.
It's in a way even an irrelevant statement, because the question whether a gauge particle has a positive or negative spectral function in the ultraviolet, and you can now go to I mean, any perturbative theory is a question of the anomalous dimension. And last I looked, the anomalous dimension of a gauge particle depends on the gauge. And I can even change its sign with changing the gauge. So while I understand where you come from, for me, it does not really make sense because I can also change the sign of the anomalous dimension of the graviton.
Okay.
Right? So I mean, what really makes sense is if you want to make this, statements about having poles in the complex plane, which for S-matrix elements is really bad, is you have a scattering, which means you already have a vertex. And that vertex is multiplied by the propagator of the transmission particle, let's assume a graviton. So what you really have to look at is the combination of two vertices and the graviton propagator and this spectral function, which is again an entirely different element. So unfortunately, in non-perturbative quantum gravity, because this means that also your vertices are quite non-trivial, the problem of distinguishing things which are unitary or not is a bit more complicated than staring at the propagator of the fluctuation. It's just simply more difficult. And I'm not saying that we have solved this. I'm saying, this complication I'm talking about is one of the problems one has to face. But now it's again the whole time about asymptotic safety, and I started with saying something about causal sets in a way.
But if you compute the S matrix, you have infrared divergence or not?
If we compute the S matrix, in the way we have computed it, we of course see in the graviton scattering, we see massless excitation.
You get infrared.
Yeah,
So you get
the
the
massless
infrared divergence as the usual one.
Yes, absolutely.
Okay, it's
You're for linear divergence.
Oh, now.
We cannot wait for a new flight. I'm sorry.
I have to move out.
Chapter 4, we should probably wrap things up. Let's thank all the panelists for their participation.